Hi everyone, this is the topic, the unit circle. In this topic I'm going to cover all of the theoretical trig for the International Baccalaureate course Maths Standard. So we're going to go through radians, sectors, the unit circle, angles of any magnitude, and then finish off with trigonometric graphs. So let's begin with radians. And we can either measure angles in degrees or radians, and degrees you should be fairly familiar with. Now, a degree is a measure of turning, like 30 degrees, 60 degrees, etc., whilst a radian is a measure of how far an object has moved on the circumference. So here's our degree measurement here, and this here, this distance along the circumference, is the radian measurement. And we define 1 radian to be the distance travelled divided by the radius. Okay, so if that was 1 or exactly the same length as this radius here, then that's going to be 1 radian. So if we take an entire circle like this, we've got 360 degrees at the centre, and on the circumference we've got 2 pi r. So recall that we're going to do the distance travelled around the circumference and then divide it by the radius, so that's 2 pi r divided by r, which gives us 2 pi. And so this is radians here. 2 pi radians is equal to 360 degrees. You can see here that I've written a little c, and that's a symbol for radians. So 360 degrees is equivalent to 2 pi radians. Simplifying that down, we have this relationship. 180 degrees is equal to pi radians. If we want to convert a radian measure to degrees, we simply substitute 180 degrees for pi. So here's our first example, pi on 3 radians. So instead of the pi, I'm going to put the 180 in. So that's 180 divided by 3, which is 60 degrees. Now what we're really doing here is multiplying by 180 on pi. So imagine taking this and multiplying it by 180 on pi. The pi's cancel out. It is useful to remember this. I'll show you an example shortly. But if you're given an expression, a radian, with pi in it, this is the simplest way to do it. Here's another one. So instead of the pi, I'm going to write 180. So that's going to give us 108 degrees. Now this one here, 1.05 radians, I can't substitute for pi because there isn't one. So in this case, I'm going to have to remember this rule. So I multiply by 180 on pi, and then I put it in the calculator, including pi as 3.14159, etc. So calculating that, I get 60.2 degrees. Now, this is not given for you on the formula sheet, so you've got to find some way of memorizing it. If we want to convert degrees to radians, then we use a similar trick. We're going to take our number and write it as a fraction of 180. So I'm going to write 45 over 180, and then I'm going to put the pi in at the end. Okay, and so what we're doing here is multiplying by pi on 180, which is the inverse of the previous example. So we've got 45 on 180. I want to simplify that down, and it's going to become pi on 4. Here's another one, 270 degrees. So I'm going to write it as a fraction of 180 and then put pi next to it. And then simplify this down. This is 3 on 2. So that one there is 3 pi on 2 radians. And just like before, they might give you something quite revolting, 6.5. I can still use this method like that. I could tidy that up into a fraction. I just need to double the top and the bottom, or I could put it all in the calculator and just do it as a decimal. So I can either write it as 13 pi on 360 or 0.113 radians. Let's move on to arc length and the area of a sector. So recall that the formula for the length of an arc in a circle of radius r is theta on 360 times 2 pi r. So let's have a look where that came from. Here we've got the full circumference, and this is a proportion of the circumference. So it depends what the angle is that I want. Now we know a bit of this, don't we? We know that 360 degrees is 2 pi. So I can substitute that in there, and these two will cancel out. And so I get this nice little formula L, or the arc length, is equal to theta r. That's providing this theta is in radians. And there it is on the formula sheet for you. Here's an example. Find the arc length and perimeter of this sector. So you can see we've got 2 radians at the center here. So to find the arc length, I'm just going to do L is equal to theta times r, and it's really simple. I go 2 times 3 is 6. So this is 6 centimeters around here. I can't do this if it's in degrees. I'd have to use the other formula. But see how simple it is when it's in radians? That's the arc length. If I want the perimeter, I've got to go all the way around the shape. So I've just got to add 3 and add 3. So our perimeter will be 6 plus 3 plus 3, which is 12 centimetres. Let's move on to the area of a sector. So just like before, let's recall that the formula for the area of a sector in a circle of radius r is theta on 360 times pi r squared. And just like before, we're going to make that substitution. 360 is equal to 2 pi. Substitute it in. Only the pi will cancel out this time. And we're left with this formula. The area of the sector in a circle of radius r is a half theta r squared, providing theta is in radians. And there's the formula on the formula sheet for you. Here's an example. See, I have radians for my angle, and I have a radius of 4.2 millimeters. So here's our formula, half theta r squared, substitute it in, half times 7 pi on 6 times 4.2 squared, and in the calculator gives me 32.3 millimeters squared. So let's finish this section with area of a segment. Now a segment is a slice of a circle, like this yellow part here. And if we want to find the area of a segment, then firstly we're going to find the area of the sector, which is this here, and then find the area of the triangle, and then subtract the area of the triangle from the area of the sector. Find the area of the segment highlighted below. So let's begin by finding the area of the sector, and I'm going to use this formula. And I do have this angle in radians, so I'm just going to substitute in half times pi on 3 times 4 squared, which is 8 pi on 3. Now to find the area of this triangle, we're going to use the formula half AB sine C from trigonometry. So A and B are going to be 4 centimeters, and C is this angle here. And I'm going to put it in radians. So this is one time that's really important that you put your calculator in radians. When you enter that, more than likely your calculator will give you the answer as an exact value, and so we're going to leave it like that. And now all we have to do is the subtraction. 8 pi on 3, take away 4 root 3, and if you want an approximate value, it is 1.45 centimeters squared. So in this section, we're going to move back to the more theoretical trig, and we're going to look at the unit circle and develop some of the relationships between sine and cos. So consider the unit circle that's below. It's centered at the origin, and unit circle means it's got a radius of 1. So here I've drawn a point, an arbitrary point xy. Remember, this is the x coordinate, so that's that distance, and this is the y coordinates. We can see a nice little triangle here with x along the bottom here, y up here, and 1 on the hypotenuse. So the value of sine theta is going to be opposite over hypotenuse, which is y. The value of cos theta will be adjacent on hypotenuse, which is x. And we'll write that up there. So x has become cos theta, and y has become sine theta. Now in the second quadrant, cosine becomes negative, but sine is still positive. So now we've taken the theta all the way over here. This distance is negative, that's negative x, but y is still positive. Down here in the third quadrant, both sine and cos are going to be negative here. So this is negative y, and this is negative x. And in the fourth quadrant, cosine is now positive because x is positive, but sine remains negative. And you can see that here. So as the point moves around that wheel, it traces out the sine curve and the cosine curve, and you can see it goes through being positive and negative, and then back to positive, and then back to negative. So let's have a look at that in more detail. So as this point moves about the unit circle, it traces out this curve. So in the first quadrant here, it's positive. Second quadrant, positive. Third quadrant, negative. Fourth quadrant, negative. Here's cosine. Starts off positive. Second quadrant, negative. Third quadrant, negative. Fourth quadrant, positive. But there's something else here. Can you notice the symmetry of this curve? There's a lot of points along here where they're equal to one another. Here it's equal to 1, here it's equal to 1. Here's 2 zeros. But also this point here is equal to this point here. So we're going to have a look at that in the next couple of slides. So let's look in more depth at these relationships. We're going to start in the second quadrant, which is the obtuse angles. So this angle here is 180 degrees minus theta. Now let's start with sine. So we worked out before that in this quadrant sine will be positive, okay, because it's to do with this y coordinate here, and that's positive. So sine of 180 minus theta is going to be exactly equal to sine theta. How about cos? Remember we said cos is negative over here? Now here's the thing, it's actually going to be equal in magnitude, so cos theta will be the same size as cos 180 minus theta, but they're going to be different signs, okay, because this one here is going to be negative. Now tan we haven't discussed, but tan is opposite over adjacent, and so opposite is the y and adjacent is the x, so it's actually also going to be negative because the x is negative. So same magnitude, different sign. Here's the third quadrant. So in this case down here, now sine has become negative, hasn't it? So it's down below the x-axis, the y is negative. So it's negative y on 1, which is negative sine. Same magnitude, these two things, different signs. Cos is still negative as well because it's negative x, but tan is now going to become positive. So negative y divided by negative x, those negatives will cancel out and gives us positive tan. And finally the fourth quadrant. So beginning with sine, y is negative, so it's negative y on 1, so it's negative sine theta. Cos is positive, okay, because x is positive. And tan is going to be negative y on x, so it's negative. Now that's an awful lot to remember, so we can use a diagram to remember the signs for the trig ratios for angles of any magnitude. So it looks like this. So in this first quadrant, all of them are going to be positive. In the second quadrant, only sine will be positive. In the third quadrant, only tan will be positive. And in the fourth quadrant, only cos will be positive. So just writing those as just capital letters, you can remember this as all stations to central, or all students take chemistry, or the cast diagram. So it depends probably which part of the world that you learn this in. So when I was growing up in Tasmania, I learnt it as the cast diagram, and then I went to senior school or senior high school in New South Wales, and there it was known as all stations to central because of Central Railway Station. So teaching in Hong Kong at the moment, you've got central, so you could probably remember all stations to central. Now, the only other thing to remember is that this is for angles of theta. These are angles of 180 minus theta. This quadrant is for angles of 180 plus theta, and this one is angles 360 minus theta. Here's an example. It's known that sine 42 is equal to 0.669. Without using a calculator, write the values of sine 138. So we firstly need to figure out what quadrant that's in. That's an obtuse angle, so it's going to be up here in the second quadrant. So remember, all stations to central. So we're sitting in this quadrant here. 180 minus 42 is 138, and sine will be positive. So it's going to be exactly equal to sine of 42, which is 0.669. Sine 222 is sitting in here. This is 180 plus 42. So in this case it's going to be negative. Sine 318 is in here. It's 360 minus 42. And again, sine will be negative. And I've just thrown in a curly one. Sine 402. Now that's sitting up in here. This is 360 plus 42 gives us 402. So we're back in the first quadrant. So in that case it's going to be equal to sine 42, which is 0.669. Now just before we move on, it's really important that you use these boundaries properly. So it's 0 plus the angle, 180 minus, 180 plus, and then 360 minus. We never do the 90s or the 270s, for instance. So since sine and cos are periodic, if we add 360 or 2 pi radians to any angle, then the ratio will remain unchanged. So we can write sine of theta plus 2k pi will be equal to sine of theta. I know this is a little scary, this notation. So this just means if I take any angle and add 360 to it or 2 pi to it, it's going to stay the same. Okay, and it says that k has to be an integer here. Similarly for cos. Tan's a little different. It repeats every 180 degrees or pi radians. So we can write just k pi for tan. So tan of theta plus k pi would be equal to tan of theta. Let's move back to the graphs. So this is the graph of y equals sine x for 0 is less than or equal to x is less than or equal to 2 pi. You can see I've moved away from degrees into radians. So remember 2 pi is 360, pi is 180, pi on 2 would be 90, and 3 pi on 2 is 270. You can see with sine how it goes through one full cycle in 2 pi, and that's called its period. So the period is how long it takes until it repeats itself. So the period for sine, and for cos for that matter, is 2 pi or 360. The amplitude is the height of the graph above its equilibrium position, which is here, 0. So the height of the graph here is 1. So here's cos between 0 and 2 pi. And again, just like I said before, the period is 2 pi and the amplitude is 1. The height above the equilibrium position is 1. We haven't looked at tan. Tan's a bit of a weird graph. As I said, it repeats every 180 degrees or pi radians, and it heads off to infinity here and has an asymptote at pi on 2 and another asymptote at 3 pi on 2, and there'd be another one here at 5 pi on 2 because it's also periodic. And that's because tan is actually sine divided by cos. We're going to go over that in the next video. And so there are occasions where we're dividing by 0. And of course, when you divide by 0 anytime, you're going to head towards infinity. So that's why we get these asymptotes. You don't have to really do much with the tan curve in this course. It's mostly sine curve and cosine curve. Now, trig functions can be transformed like any other functions, and we can write the general sine function like this. So you can see here I've got sine, and I've got a number or a constant at the front, and that's going to affect the amplitude, so the height of the graph. Inside here I have a number in front of the x, and that's going to affect the period. I'm going to talk more about that later on. This minus c here is going to be a horizontal transformation, so it's going to shift it this way, and this one's going to be a vertical transformation, so it'll shift the whole graph up or down. So let's look at an example. How is y equals 2 sine, and then brackets 3, brackets x minus pi, plus 1, different to y equals sine x? So in this case we've got to do 4 transformations. This one, this one, this one, and this one. We're going to start with this. Now that's going to change the amplitude. And the 2 is going to make it twice as tall, so it's kind of going to stretch it. So instead of having an amplitude of 1, now it's got an amplitude of 2. So it goes out here to positive 2 and down to negative 2. Next one we're going to do is this plus 1. And that's a vertical transformation, so it's going to move the whole graph up by 1. So it was starting at 0 before, now it's starting at 1. and this has become the equilibrium position. Okay, thirdly, we're going to look at this 3. Now the 3 changes the period of the graph, and it makes it go 3 times as fast. So normally it gets through one cycle between 0 and 2 pi. Here it's going through 3 times. Here's a useful little formula. The period is equal to 2 pi, that's the normal period for sine, divided by b. And b is the constant or the number that's in front of the x. So you can see how I've just divided there by 3. And what this period means is that that's how long it takes to get through one cycle. So if we find 2 pi on 3, that's like 2/3. So that's around about here. That's how long it takes the graph to get through one cycle. Do you see? And then finally we're going to have a look at this shift here. And this creates a horizontal transformation. And that means the graph is going to start, if you like, at pi. So we just solve that equal to 0. So it shifts it over to what makes 0. So it's starting here at pi. So I've shifted it all over. You can see that it's going to 3 pi. Now we don't want it between pi and 3 pi. We want it between 0 and 2 pi. So we're going to have to fill it in back here and then chop it off here like this. So the domain is going to be between 0 and 2 pi, and you can see how we've filled it in here and it's been chopped off here. So as I mentioned before, the tide can be modelled using trig functions. They'll usually tell you whether you're using sine or cos, but we won't ever use tan because we don't have asymptotes, with tides. Thank goodness. So let's have a look at this. We've been given that x is equal to 5 plus 4 cos of 4 pi on 25t. A few differences. Our dependent variable is x, which is the height of the tide, and our independent variable is t, which is the time in hours after the first high tide. Question A, what's the highest point? There's a number of ways to do this. Probably the easiest is to realise that cos, the maximum cos ever gets to is 1. So if that gets to 1, that thing there, then the maximum of this whole thing is going to be is 4. So therefore, the highest tide will be 9 metres. Now the amplitude is always given by this number here. Regardless of what's going on around, it's going to be the number in front of the trig function. So that's 4 metres. It's also the midpoint between the highest point and the lowest point. So again, remember cos, the least it will be is -1. 5 take away 4 is 1. And you can see 9 metres, 4 metres, 1 metre. So that's another way to do it. C. When is low tide? It's not asking what is low tide. We just worked that out. It's 1 metre. It's when is low tide. We're just going to do exactly the same as what we just did. Solve this cos 4 pi and 25t equal to -1. So if we want to solve this, we need to think about when is cos, the normal cos, equal to -1. I always draw just a quick graph. So here's cos here, and it's hitting -1 here at pi. So that means that all of this is going to be equal to pi. And now just take these over the other side. 25 comes up the top, 4 pi goes down. And when you sort that out, cancel the pi's, you get 6.25 hours. So it's going to be 6.25 hours after the first high tide, which we don't know when it is. So that's the answer. D, what is the period? So we're going to use that formula, remember, 2 pi on b. And b is the number that's in front of the pronumeral here. So it's 4 pi on 25. So I'm going to put that in here. Working that out either by hand or on the calculator is going to give us 25 on 2 or 12.5 hours. Now, it says here, why was cos chosen instead of sine? Well, that's an interesting question, isn't it? Remember the difference between cos and sine? So sine starts at the equilibrium position and cos starts at a maximum. Remember how it says that the time t is going to be the time after the first high tide? Let's just draw the graph here and make sure you understand. So here's sine starting at the equilibrium position, and cos starts up here. So that's why they chose cos. Here's another example. The mean monthly temperature for Hong Kong over a 12-month period is given by that data there. model this data using the general sine function. So there it is, y equals a sine, and then in brackets b, and then brackets x minus c, close brackets, plus d. All right, first thing we're going to do is plot that. Looks like this. Looks interesting, doesn't it? Does look like a sine curve. Now this seems like a really difficult question, and it's not easy, but in an exam it'd be scaffolded and you'd be led through it. But we would always start by finding the equilibrium position and the amplitude. Now, I'm not going to put the data up again, but the maximum was 29 and the minimum is 16. So when we're finding the equilibrium position, we're finding the center of the data, if you like, or the line about which this is oscillating. So we're going to take the max and the min and find the average. And so the equilibrium position for this temperature is 22.5. Now the amplitude is nice and easy. It's either this distance here or this distance here. So you can either do the maximum, take away the equilibrium position, or find the distance between minimum and the equilibrium. So our amplitude is 29 take 22.5, which is 6.5, and that is A. Okay, the next thing to find is this D here. Okay, and that's how far the graph's been shifted up. So the equilibrium position is normally 0, but in this case it's 22.5. So it's moved up 22.5. So that's D. So you can see how I've put those values in. The next thing we're going to find is this one here, which is related to the period, remember? Now, it takes 12 months to get through a cycle. So what we're going to do is make that 2 pi on B equal to 12. And we're just going to solve for B now. So B is going to equal pi on 6. So I'll put that in here. And finally, we've got to find the value C. The easiest way to do that is just to substitute a point in. So let's pick 116, which is the temperature in January. Substitute it in. Now, your calculator will most likely solve this if you put it in correctly and use equation solver. So it tells you that X, which in this case is C, is going to be equal to 4. But suppose they were nasty enough to give this in the non-calculator, we would take our 22.5 across, divide by 6.5, solve this. So we need to find inverse sine of -1, and I'm going to put that as negative pi on 2. Take our pi on 6 over the other side, so I'm multiplying by 6 on pi, and then solving, and I get C is equal to 4. So just before we finish, we should test a point, make sure that we're right. So let's check X is 5, which is May. Substituting that in and working it out, I get 25.75 degrees, and May's temperature was 26 degrees. So all good.